The objective of this lab was to use observations about the motion and collision of two billiard balls to make predictions of the velocity and future displacement of a system using a computational model. Additionally, through graphical analysis using the momentum principle and conservation of momentum, the system of the two billiard balls was determined to be interacting with forces from surrounding objects. In order to come up with these conclusions, I first simulated the collision of two pool balls in a game of pool. I had a friend roll one ball towards another ball at rest through an approximately straight line. I repeated this simulation on 3 different surfaces of different textures. These included a pool table, an ice hockey table, and a carpeted floor. I then imported the videos into Tracker to record measurements of the observations. By plotting the position data of the balls individually, I was able to make inferences about the total momentum of the system on each of the 3 surfaces. By plotting the position versus time data of the 2 known masses, the velocity of the system can also be determined. Newton's second law, otherwise known as the momentum principle, relates the change in velocity for a system of given mass, or the momentum of an object, to the net forces acting on the system times the duration of the interaction. Changes in velocity for a system, as supported by the momentum principle, give insight to the forces acting on the system. The momentum for a system is the vector sum of all the momenta of the objects in the system. The conservation of momentum describes that momentum cannot be created nor destroyed. Instead, it is transferred from one object to another. Therefore, the sum of the momentum in the system and the momentum of the surroundings is equal to 0. An isolated system is one that has negligible interactions with the surroundings. Because momentum cannot be transferred from the system to the surroundings, or the reverse, momentum is constant within the system. Therefore, for an isolated system of 2 billiard balls that start out with an initial momentum held entirely by the momentum in the first moving ball, should experience no changes in total momentum with the collision of one ball to another, since it is entirely conserved. By graphing the momentum of the system as a sum of the individual momentums of the 2 balls in the system, a constant momentum over time, t, would suggest an isolated system, whereas a change in momentum would suggest interaction with outside forces. Using position data for the balls 1 and 2, I created a code that takes measurements made from observations in Tracker and models these changes in position while comparing the predicted positions of an isolated system that starts out with the same initial velocity. The code also graphically displays the change in momentum of the balls individually and together as they act as an isolated system. While graphical analysis would provide insight as to the interactions acting on the system, there were areas of potential error in making observational measurements. In making measurements of the observed motion in Tracker, it was difficult to mark the displacement of the ball as it moved slightly into the plane along the z-axis, because in Tracker I could only mark x and y positions. Additionally, as seen as a comparison of the predicted motion and the observed motion, the ball doesn't seem to move in a linear fashion. This is because some of the movement is absorbed in the rotation of the ball. Variance in the comparison of the predicted movement of the balls given an isolated system as compared to the actual observations convey that the balls experience additional forces from the surrounding. This is also seen through graphical representation of the momentum of the system over time. The conservation of momentum upholds that for any isolated system, momentum is influenced by the forces acting upon it to either transfer in or out momentum, and that for an isolated system, there are no forces from the surroundings that influence the momentum of the entire system. Any changes that do occur for the momentum of a system exist in the transfer between objects within a system. Therefore, for our isolated system consisting of 2 billiard balls, momentum should remain conserved for the entire system before and after a collision. Because on each of the 3 surfaces, as indicated by the blue lines in the graphs, momentum varies, and more specifically decreases through the duration of the ball collision. This variation concludes that the system of the 2 balls is not isolated and is subject to external forces. But where could these forces come from? In looking at the system consisting of the 2 balls, the only other contact they have then with each other exists with the air particles and the table surface on which they rest. Because the balls are moving at such slow speed, we can consider the forces from air particles or air drag as negligible. This leaves us with the forces from the table. Friction force results from the interaction of the resistance of one surface to the relative motion of another. More specifically, for a system, we can consider static and sliding friction. Static friction exists for 2 objects that are not moving relative to one another. It is the same friction that keeps a heavy box from sliding down a shallow slope. Kinetic friction exists for 2 objects that are moving relative to one another. From a basic definition, it is assumed that for each of the surfaces, kinetic or sliding friction acts to slow down the balls and explains the gradual decrease and the momentum of the system. But because the balls move on a smooth, rounded surface, their contact with the table is instantaneous and considered not moving. Therefore, we can attribute both kinetic, sliding, and static friction as potential interactions with the billiard ball system.